Imagine a frozen object that has traveled through the darkness between stars for millions, perhaps even billions, of years before briefly entering our solar system. It carries material formed around another star, preserving a record of a place humanity has never seen. That is exactly why the discovery of 3I, Atlas, the third confirmed interstellar object ever detected, has generated enormous excitement among astronomers. Unlike ordinary comets that formed alongside our Sun, 3I, ATLAS began its journey in an entirely different planetary system. Long before Earth existed, it may have been ejected by the gravity of giant planets or passing stars, beginning an incredible voyage across the Milky Way. For decades, scientists believed interstellar visitors would be almost impossible to detect. That changed in 2017 with the discovery of Oumuamua, the first known object arriving from another star system. 2 years later came Comet 2I, Borisov, whose icy composition confirmed that material from distant planetary systems could occasionally pass through our own. Now, 3I, ATLAS has become the newest member of this extraordinary family. As soon as astronomers confirmed its unusual trajectory, observatories around the world turned their attention toward it. Among the most powerful instruments available is the James Webb Space Telescope, whose infrared capabilities allow scientists to study distant objects in remarkable detail. Unlike visible light telescopes, Webb can detect heat signatures and analyze the chemical fingerprints hidden within dust and gas surrounding icy bodies. These observations help researchers determine what an object is made of and how it has changed over time. Early studies suggest that 3I, ATLAS contains a mixture of ice, dust, and carbon-rich materials similar to what is found in many comets. However, because it formed around another star, its precise chemical makeup could reveal important differences between our solar system and distant planetary systems. Every spectrum collected by Webb is like reading a page from an ancient history book. Scientists search for water ice, carbon dioxide, carbon monoxide, methane, and other frozen compounds that formed under conditions far from our own Sun. Comparing these materials with those found in solar system comets helps researchers understand whether planet formation follows similar patterns throughout the galaxy, or whether every stellar system evolves differently. Another remarkable feature of 3I, Atlas is its speed. Unlike planets and comets that remain gravitationally bound to the Sun, this object is simply passing through. It entered our solar system on a hyperbolic trajectory and will eventually continue its journey back into interstellar space, never to return. That makes every observation incredibly valuable. Astronomers have only a limited window to collect as much information as possible before this cosmic traveler disappears forever into the darkness between the stars. But perhaps the most exciting aspect of 3I, Atlas is what it represents. It is more than a comet. It is a messenger from another star system, a natural sample of material that formed light years away, offering scientists a rare opportunity to compare our own cosmic neighborhood with distant regions of the Milky Way. Each observation helps answer fundamental questions. How common are planetary systems like ours? Do distant stars produce similar icy bodies? Could interstellar objects transport complex organic molecules between stellar systems? These are questions that researchers are only beginning to explore. In Part 1, we explored how 3I, ATLAS became only the third confirmed interstellar object ever discovered passing through our solar system. Unlike ordinary comets, this remarkable visitor formed around another star, making it one of the rarest natural objects humanity has ever studied. Now the big question is, why is this object so important? The answer lies in its origin. Every planet, moon, asteroid, and comet carries a record of the environment in which it formed. Since 3I, ATLAS was born around a distant star, it preserves chemical information from a planetary system completely different from our own. It's almost like receiving a sealed package from another corner of the Milky Way. Scientists are using powerful observatories, including the James Webb Space Telescope, to analyze the object's composition. Webb's infrared instruments can identify molecules by studying the light they absorb and emit, revealing clues about the ice, dust, and gases locked inside the object. Researchers are particularly interested in compounds such as water ice, carbon dioxide, carbon monoxide, methane, and complex carbon-based molecules. These materials help scientists reconstruct the conditions that existed when the object formed millions or even billions of years ago. One fascinating possibility is that interstellar visitors like 3I, ATLAS carry organic molecules, the carbon-based building blocks that play an important role in the chemistry of life. Finding organic compounds would not mean that life exists on the object. Organic molecules are common throughout space and can form through entirely natural processes. Even so, studying them helps scientists understand how the ingredients for life may be distributed throughout the galaxy. This idea connects to an interesting scientific hypothesis known as panspermia. Panspermia suggests that some of life's chemical ingredients, or under certain versions of the idea, even microscopic organisms, could potentially travel between planetary systems aboard rocks, comets, or other space debris. At present, there is no direct evidence that interstellar objects spread life between stars. However, studying visitors like 3I, ATLAS allows researchers to investigate whether they transport complex chemistry across the galaxy. Every new observation adds another piece to that puzzle. The discovery also has practical importance. Future generations may develop spacecraft capable of intercepting interstellar objects during their brief passage through our solar system. Unlike ordinary comet missions, such spacecraft would have only a short time to approach, observe, and collect data before the object continued its journey into deep space. Designing these missions will require extraordinary precision. Navigation systems must account for extremely high speeds, constantly updated orbital calculations, and rapidly changing observation opportunities. Advances in autonomous spacecraft technology could eventually make these ambitious missions possible. Imagine a probe flying alongside material that formed around another star. Instead of studying distant planetary systems through telescopes alone, humanity could directly examine fragments created light years away. That possibility makes 3I, ATLAS far more than a passing comet. It represents a glimpse into the incredible diversity of our galaxy. Every star forms under slightly different conditions. Every planetary system evolves in its own unique way. By comparing objects from different stellar neighborhoods, astronomers can better understand how common, or how unusual, our own solar system truly is. Although 3I, ATLAS will eventually leave the solar system forever, the scientific knowledge gained from its brief visit will remain. Its journey reminds us that our solar system is not isolated. From time to time, visitors from the vast space between the stars arrive carrying stories written in ice, dust, and ancient chemistry. And somewhere beyond our view, countless more interstellar travelers are already crossing the galaxy, waiting for future generations of astronomers to discover them. With every new detection, we move one step closer to understanding not only where these mysterious objects come from, but also how our own place in the universe fits into the much larger story of the Milky Way.